The previous class, that is a semi-classical treatment part 2, we have seen in detail about the emission and absorption process. In this class, that is a semi-classical treatment of radiation part 3, we will see the electrical dipole transition in detail. Electrical dipole transition, this is going to be a very short lecture. In most of the practical cases, the wavelength of radiation is very large compared to linear dimension of wave function, which describe the particle k dot r is equal to 2 pi by lambda r. This you know very well that r is atomic distance, which is very much less than the wavelength of light, that is which varies from 400 nanometer to 800 nanometer. Hence, 2 pi r over lambda is very much less than 1, as r is very much less than lambda. So, the good approximation is e power ikr is approximately equal to 1. Then we have seen that integral T3R UK star e power ik dot r del a un. This I have explained in my previous class that del A represents the propagation along the polarization vector A. A is the vector potential into UN. Since we have assumed UK, e power I k dot r is equal to 1, that is, this is 1, we can ignore this term. So this will become integral T3 R UK star del A UN, which is equal to, we have seen from previous case, this can be written as, that is, we are changing del into del operator into momentum. So we know P is equal to minus IH cross del. So this PA we are changing into this del. I mean this del operator we are changing into I over H cross PA. I over H cross this PA. So this will become 1 over IH cross K prog K PA into get n. This is in Dirac notation. This is in the integral form. That means integral T3R UK star del A UN, which is equal to 1 over H cross prog K PA del n. So we will see what will happen to this expression. So we have seen the integral D3R UK star del UN is equal to 1 over H cross KPAN. Now we know that P is equal to mass into velocity, that is mass into TR by TT. Hence we can write this expression as 1 over M KPAN, that is get n, which is equal to, because if you bring m this left hand side, p divided by m is equal to tr by dt. That's what I have written here, that is t by dt k r n. uh, See, the time derivative, as usual in the time dependent perturbation theory, time dependence comes in the exponential term, that is e power I omega k n t. So if you differentiate that t by dt, you will get I omega k n, and this term will be kept as it is. That is k r n can be kept as it is, and this t by dt is replaced by I omega k n. Now you remember that KPAN is equal to this M will go into the right hand side. So you will get this M remaining all the term, that is M I omega Kn and KRN will come here. So this is about KPAN. You will get this one. Now you come back to this integral. That is integral T3R UK star del un, which is equal to uh, 1 over h here. You have 1 over h cross, and this one KPAN. Sorry, this will become KPAN. KPAN is mi omega kn krn. This 1 over IH cross comes from here, and if you replace this KPAN, that is KPAN, which I have shown in the green color part, you will get this one. So you substitute this here. You will get, in addition to 1 over IH cross, you will get uh, M I omega Kn KRN. This I into I, you will get I squared, which is equal to minus 1. So this will become minus M pi H cross omega Kn KRN. We will see what will happen to this expression. So just now we got this expression. Here I like to highlight one important point, that get k and get n are the stationary state. That is a time. So the time dependence comes through the factor e power I omega t. These are the get k and get n are the stationary state. Hence, the time dependent factor comes from, it has to comes from e power I omega t. Thus, in the dipole of approximation, the transition rate at time tau is 1 over tau modulus of ak1 whole square. Just this we have seen in the in previous case, that is emission and absorption. That is semi-classical treatment of radiation part 2. We have seen this expression. Now here, this is this modulus square. This one exactly this one is equal to this minus m h cross omega kn. Kn krn. That's what I have substituted instead of this one. This integral, sorry, this integral I have substituted this one. I have substituted this one from the first equation. So from the first equation I have substituted, which is equal to minus m h cross omega kn uh, krn krn modulus square, of course. So here, if you note carefully, because my negative sign will become positive because it's a modulus square, this m squared will cancel with this green color bond m square, and omega kn squared will cancel with this omega kn squared, of course. Then you will get h cross squared. So 4 pi squared e squared over h cross squared c I omega kn, and this term, that is krn modulus square. So we will end up with this expression. We will see what will happen to this expression. In the previous slide, we have seen this is the square of the probability amplitude per unit time. That is probability per unit time, which is equal to 4 pi squared e squared over h cross squared c. I which is a function of omega km modulus krn whole square. So here you notice that this e squared, you bring this e squared inside this tag notation, that is inner product. This will become e r a. that is KERAN modulus square, where RA is the component of R along A naught. This is called electric dipole transition, as only matrix element of electric dipole moment ER is involved. E into R is the electric dipole moment. Only this involved. This is in the matrix form. So this is called electric dipole transition. Thank you very much for watching my videos and supporting me continuously. If you have any question, kindly send to the following mail ID vasum, that is vasumku at gmail.com. I will answer at the earliest through mail or YouTube videos. This will help me to improve my lecture. Thank you very much for your cooperation. My YouTube channel ID is www.youtube.com/c/vasuv physics. Thank you for your support.